So, relative atomic mass. If we have a look at these relative abundances and their relative masses, we can then work out a relative atomic mass. Relative atomic mass is equal to the average relative isotopic mass of one atom. Okay, but it needs to take into account the abundance of that atom. And it's worked out with a formula like this. So, relative atomic mass equals the relative mass of isotope 1 times its percentage abundance plus the relative mass of isotope 2 times its abundance. That gets divided by 100. I'm going to show you an example. So let's look at oxygen. Oxygen has 3 naturally occurring isotopes, 16, 17, 18, and these are the exact relative isotopic masses of those isotopes. We need to consider the abundance of these in nature. So which one of these occurs more? If we have a look here, oxygen 16, 99.76, so the majority of oxygen is this particular isotope, isotope 16. However, there are small amounts of oxygen 17 and oxygen 18 that exist. 0.04% is oxygen 17 and 0.2% is oxygen 18. We have to take those into account when we're working out our relative atomic mass. So we use the formula. Isotope 1's relative mass times its percentage abundance. Isotopes 2's relative isotopic mass, which is 16.99, times percentage abundance, which is 0.04. And I've written them down here for you. Last one, isotope 3, we've got its relative mass, which is 17.999, multiplied by 0.20. So each isotope, you're just multiplying the relative abundance percentage by the relative isotopic mass. You add those together and divide the grand total by 100. So if it's got 5 isotopes, you'd work this out for the 5 isotopes. If it's only got 2 isotopes, you'd work that out for the 2 isotopes. So our answer is 16.0. 16.0. Does this look familiar? It should. When we look at the periodic table, the mass number of oxygen is 16.0. So the relative isotopic mass of an element is equal to the mass number on the periodic table. So let's have a look at a second example here. Natural chlorine consists of 2 naturally occurring isotopes, Cl35 and Cl37. And here they are on the mass spectrum graph. You can see 37 here has a percentage abundance of approximately 25% and 35 here of approximately 75%. If we read our question, we can see that. So the relative isotopic mass of Cl35, to be exact, is only 34.969. Okay, it's not exactly 35, it gets written as 35 though. Its percentage abundance is 75.91. The second, Cl37, has a relative isotopic mass of 36.967. Again, it's not quite 37, but we write it as isotope 37. Its abundance is 24.09. Abundance there, 24.09. You'll notice again that the overall abundance of 75.91 plus 24.09, the grand total there is 100%. It has to be, because there's only 2 isotopes occurring naturally. So it's asking you to calculate the relative atomic mass. So again, we use that same formula and we put in isotope 1, 34.969 is its relative isotopic mass multiplied by its percentage abundance, which is 75.91, plus isotope 2's relative isotopic mass, which is 36.966, times the abundance of 24.09, divide all of that by 100 and you get 35.45. This number here is the relative isotopic mass of chlorine, and it is equal to the mass number of chlorine when we look at the periodic table. It now makes sense why this mass number is in decimal places. This is because it is an average of the percentage abundances of each of the naturally occurring isotopes. Question 1. I'd like you to pause the video here and I'd like you to have a go at this question, please, and I will run through the answer for this. So for the relative atomic mass for lithium, you should have gotten an answer of 6.94, and for the graph of the mass spectrum, you should have drawn it like this. So the relative abundance on the y-axis, the relative isotopic mass on the x-axis, and peaks at 6 and at 7, with peaks of 92.6% and 7.4%. If you're not sure how I got those, the worked solutions are at the end of this video. Have a go now at question 2, pause the video again and work your way through that. I'll put the work solutions at the end of the video. So the answer you should have gotten for the relative atomic mass of copper is 63.6, and your mass spectrum should have looked like this, with peaks at 62.95 and 64.95, this peak being 30.4% and this peak being 69.6%. Again, the worked solutions are at the end of the video. And question 3, pause the video, have a go, I'll pop the answer up. Magnesium's approximate relative atomic mass should be 24.31, and your graph should look something like this, with peaks at 23.99, 24.99, 25.98, of 11%, 10%, and 78%. So all of those workings are at the end of this video. If you don't need to work through those, it's a slightly different type of example here. Use the data in the table below to find the relative isotopic mass of chlorine 37. Okay, so what we've been given here is the relative atomic mass of the atom, which is 35.45, but we need to work backwards from that to calculate the isotopic mass of chlorine 37. So this is a little bit of maths involved. So again, we use this formula here and we plot in the data that we know. We know the relative atomic mass of chlorine, but we don't know the relative isotopic mass of chlorine 37. So we need to solve this equation to find out what chlorine 37 is. So it's just a case of multiplying all of this out and solving for X, or in this case chlorine 37. So multiply that out and you get 2650.65. You've got your 24.20 times your unknown isotopic mass of chlorine 37. So if we subtract 2650 from both sides, we then get, and then divide by 24.2, we can work out the relative isotopic mass there of chlorine 37, which is 35.96. So have a go here at question 4, pause the video and I'll pop the answer up for you. So the answer you should have gotten for that is 107.9, which you can round up to 108. The work solution is at the end of the video if you'd like to see how I got to that answer. Question 5, again, pause the video, have a go at that. And the answer you should have gotten is 10.2. And if you have a look at the periodic table, you would then think that the answer would be boron because that is closest. Work solution again is at the end of the video. And question 6. Again, pause the video, read the question carefully. I'll put the answer up. And the answer you should have gotten is a relative isotopic mass of 70. Again, those work solutions are at the end of the video. Example 4. You will get a picture that looks something like this, and it's going to ask you to calculate the percentage abundances of each of these 3 isotopes. There is no labelling on the side here, so how do you go about it? You use a good old-fashioned ruler. Okay, so you've got a ruler here. You can measure up that the top peak here comes to 7.5 centimetres and that these 2 peaks are 1 centimetres each. So if you measure exactly, you get 7.9 centimetres for magnesium 24, 1 centimetre for magnesium 25, and 1.1 centimetre for magnesium 26. Now that we know that, we can turn those into percentages of the total height. So the percentage of the isotope of 24 magnesium is 7.9 over the total of all of those heights, which will equal 79%. And you work out the other isotopes exactly the same way. You're just working that as a percentage of the overall length of those peaks. Last but not least is when you don't know the percentage abundance of the 2 isotopes at all, but you do know the relative atomic mass. And this is probably the hardest one mathematically. Okay, let's have a look at the question first. Copper has 2 isotopes, copper 63 and copper 65. Copper 63 has got a relative isotopic mass of 62.95 and copper 65 has a relative isotopic mass of 64.95. You know that the relative atomic mass of copper is 63.54, but you need to calculate the percentage abundance. So let X be the percentage abundance of copper 63. So therefore, the percentage abundance of copper 65 has to be 100 minus X, because we know that the 2 of them added together need to equal 100%. Okay, once you've got that bit, it's all just maths from here. So again, our formula, which equals then 62.95 times X plus 64.95 times 100 minus X. You need to work that out mathematically and solve for X. So you just multiply that second part of the equation out and work your way through and solve for X that way. And X equals 70.5. So that means that the percentage abundance of copper 63 is 70.5, and so the percentage abundance of copper 65 has to be 100 minus 70.5, which equals 29.5. That's going to be the hardest one of those that you get. The rest of this video is just work solutions for questions 1 through to question 6. So if you've gotten those right, you don't need to watch any more of this video. If not, here are the work solutions for you. So, lithium exists in 2 isotopic forms. So lithium-6, which has an abundance of 7.40%, and lithium-7, which has an abundance of 92.6%. The precise atomic masses of the 2 isotopes are 6.01512. So lithium 6 is actually 6.01512 and lithium 7 is 7.01600. Calculate the relative atomic mass. So we use the formula again. Lithium 6 relative mass is 6.01512 multiplied by its abundance, which is 7.40, plus lithium 7's details, so relative isotopic mass of 7.01600 times its percentage abundance, which is 92.6. Divide all of that by 100 and you get 6.94. The other thing you were asked to do was sketch these on a graph. Now, when you're sketching them on a graph, it's important to notice, or to put at the bottom, the relative isotopic mass, which is just transcribed, so it's 6.01512 and 7.0160, and then you want to draw in some peaks. So we've got a 7.4% here, abundance, so you need a little tiny peak here for this one, and for the other one here, lithium 7, you've got a big peak, which is 92.6%. So you can actually draw a dotted line across there and a dotted line across there if you like to show the exact abundances. Question 2. Copper consists of two isotopes, which is copper 63, which has a percentage abundance of 69.1%, and a relative atomic mass of 62.95, and the second isotope is copper 65 with a relative isotopic mass of 64.95. The question asks you to work out the relative atomic mass of copper. So we get our formula, which we know. Relative atomic mass equals isotope 1's relative mass times percentage abundance plus isotope 2's relative mass times percentage abundance, all divided by 100. We put those figures in. So isotope 1 is copper 63, which it has a relative atomic mass of 62.95 and a percentage abundance of 69.1. Second isotope is copper 65, which has a relative isotopic mass of 64.95, and the abundance we work out because one isotope has the abundance of 69.1. In total they must equal 100, so the abundance of the second isotope must be 100 minus 69.1. Now we just need to solve for that. Remember when you put it into your calculator to put brackets around it or to work these out individually first. So we get an answer of 63.6. It asks you to graph this mass spectrum. So make sure you've got your relative isotopic mass on your x-axis and your relative abundance on your y. And then you just need to plot the points. So it's 62.95, which is the first isotope, has a relative abundance of 69.1, which is approximately up to here, and the second isotope here has an abundance of 30.4, and that's been written in there to make it clear. You could also write it on the y-axis there. Question 3. Use this data to determine magnesium's approximate relative atomic mass. All the information's here. This is isotope 1 with its relative isotopic mass and percentage abundance. So we pop all of this into the equation. So isotope 1 is 23.9, 78.7, plus isotope 2, 24.99, times its abundance, which is 10.13. Isotope 3 is 25.98, multiplied by 11.17. All of that divided by 100. Again, remember to work out your multiplication in brackets first, and you'll get an answer of 24.31. To graph this, you just need to draw those peaks in as we've done before. So these are the peaks drawn in here. Remember, your relative isotopic mass is on your x-axis, your relative abundance is on your y-axis. I've put about 10% here because these are 10 and 11% respectively, these two peaks, and 80% here. To be more clear, you might choose to write them on the actual graph themselves or on the axes here. These are written in here, magnesium 24, magnesium 25 and magnesium 26. Again, to be more clear, you can write these in the bottom axes on the x-axis here. Have a go at question 4 here. You've got that in your notes. See how you go. Keep in mind that the relative abundances always have to equal 100%. Pause this and I'll run through the answer with you. Okay, so the important thing to remember here is that the relative abundances need to add up to 100%. So in this case, we know that the formula is isotopes, relative atomic mass of isotope 1 times its abundance plus isotopic mass of isotope 2 times its abundance. But we don't know the percentage abundance of the second isotope, or do we? If the entire abundances have to add up to 100%, the abundance of the second isotope is going to equal the total abundance, which is 100%, minus the abundance that we know, which is 51.8, which will equal 48.2. So we can just work that out again, and we work out that it's got a relative atomic mass of 108. Question 5. Examine the graph and suggest an element which would produce this spectrum. Show all working. Okay, so from the graph here, you can put the information into a table which has been done there for you. Isotope 1 has a relative isotopic mass of 10 and an abundance of 81.3. Isotope 2 has a relative isotopic mass of 11 and an abundance of 18.7. So we put those into the formula here. 10 times 81.3 and 11 times 18, and we get an answer of 10.2. Have a look at the periodic table and see which element comes closest. In this case, boron would be the closest. It's not exact, but it's the closest one, so we have to assume it's that element. It's got a mass number of 10.811. Question 6. Gallium has two isotopes. Gallium-69 with an abundance of 60.5, and the relative atomic mass of gallium is 69.7. So we want to find out the relative isotopic mass of the other isotope. Write down the formula straight away. Again, we know that 69.7 is the relative atomic mass of gallium. So we can pop that in there, and we can also put the information for the first isotope in. So it's gallium-69, and its abundance is 60.5. We don't know what the relative isotopic mass is. So we'll put this in as this, or you might want to use an X or a Y. And we know that the abundance has to be a total of 100, so the abundance of this unknown isotope must be 100 minus 60.5. We divide all of that by 100. Then it's just a case of multiplying this bracket out, so we'll get 100 times the relative isotopic mass of gallium here, times 60.5 times that again. Now we can just solve for the unknown. And we get an answer here of 70.